So there are 5 types of chemical bonding. What are those 5 types of chemical bonding? Mayank? One is your covalent bond. So basically you can see 5 types of solids, 5 types of compounds. 5 types. One has covalent bonds in the atoms, which can be polar and non-polar. You can hear me? Yes, which can be polar and non-polar. These are 2 types. So out of these 2, which one has low melting point, low boiling point? Polar or non-polar? Non-polar. You know how to identify them. Second is ionic solids. Ionic solids. They are made up of ions. Very strong attraction. Much more stronger than what is present in covalent. You can call them as covalent molecules. Covalent molecules. Third is metals. They are also solid, most of them, all of them except few metals. They have metallic attractions, metallic attractions. Then the fourth one is covalent network solids. What's the difference between this and this? Network solids. These have a continuous, very big network of covalent bonds like this, big network. Like covalent molecule, for example, if I give you H2S, then it has only 2 covalent bonds. You draw the Lewis dot structure, only 2 covalent bonds, right? But look at this network. It's a continuous, very big network of covalent bonds. Many, many covalent bonds. Every atom is connected to other atom by many covalent bonds. And this is the one which is strongest. Strongest. And this is the one which is covalent molecules, is the one which is weakest. So generally covalent molecules are gases, liquids, they are solids also, but they are gases and liquids. Ionic solids, again very strong. So they all are always solid. Metals are generally, all of them are solids, except few. So the strongest attractive forces are in covalent network solid. What kind of attractive forces are these? What is the name? The name is covalent bond. Every atom is attracted or is actually bonded to another atom. So they are really making covalent bonds through with each other, and that's the attraction. Covalent bond is sharing of electrons, covalent bond. Sharing of electrons. It's a real bond. It's not an attraction of partial negative, partial positive. It's a real attraction. So this covalent bond is very strong attraction. Very strong. I gave you few examples of these covalent network last time. These examples are diamond, graphite, and silica. Diamond, graphite, and silica. Out of these three, this diamond, you remember tetrahedral network? We discussed all this thing in the last class. This is your layered structure. Layers can slide over each other. These are allotropes. I gave you the word allotropes also. And what is this? Silica. In silica also, each silicon is surrounded by 4 oxygen like this. So if I don't make tetrahedral, it's actually tetrahedral like this, tetrahedral. But on the paper, I can show you like this. Now this oxygen is connected to another silicon. Now this silicon is connected to 4 oxygen again, like this. Then this oxygen is again connected to silicon. Same here. This oxygen is connected to silicon. This oxygen is connected to, you see, network of covalent bonds. So covalent network solids are very few examples. One is diamond, graphite, then silicon carbide, this one. Then aluminum nitride. If you see, look at the periodic table, they all are together. Carbon, below carbon, there is silicon. Next to carbon is nitrogen. And before silicon is aluminum, then oxygen. So you can see them, they are very closely placed in the periodic table. So they are making this network kind of bonding, and these networks are very strong networks. Very large amount of energy is needed. They have very high melting points. So please memorize all these points. Okay, now I'm coming on the next, ionic solids. So we already know how these ionic compounds are formed. One is losing, other one is gaining, that we know. But why these ionic compounds are always solids? Because of the very strong, what is the force of attraction here? The Coulombic forces of attraction, which you can measure by using this equation. Q1, Q2 over R squared. This equation. Practice this equation because I gave you this equation in the periodic trends also. So children, what is Q1, Q2 here? Charges. What is R squared here? The charges. What is R? This is R. The distance of separation. Yeah, the distance of separation between these two nuclei which are attracted to each other. Yes, distance of separation. And what's the relation between the force of attraction and distance of separation? If R is more, what happens to force of attraction? It decreases. And if R is less, the force of attraction increases. And if your Q1 and Q2 are more, Q is more, charges are more, force of attraction increases. And if charges are less, force of attraction decreases. This is very important for physical properties, for many important things about ionic compounds. In ionic compounds, there is transfer of electrons. So they are saying that if A is making an ionic compound with B, and A is acquiring plus, B is acquiring minus, out of these two, which one is more electronegative? A or B? Yes, B is more electron. That's what they are saying. Okay, when the difference in electronegativity, you remember we discussed the difference in electronegativity, is greater than or equal to 1.6, this is a very big difference, then they make ionic compounds. Then one becomes metal, other one non-metal, right? Okay, so based on this Coulomb's equation, we call this force of attraction as Coulombic forces. And it depends on charges and distance of separation. I'm giving you MgO and CaO. Can you tell me out of these two, which one has more force of attraction? MgO or CaO? So first, you check. These are ionic, right? You know that, metal, non-metal. So what is the charge on magnesium? 2 plus, 2 minus, 2 plus, 2 minus. Charges are same. So compare R. So just ignore O2 minus same. So compare the ionic radii of Mg2 plus with Ca2 plus. So which one is bigger in size, Mg2 plus or Ca2 plus? So this has more R, more R. So force of attraction in Ca2 plus will be less. So this one has strong force of attraction, MgO, like this. Okay, giving you another example. Na2O, MgO, Al2O3. Compare melting points. Melting point depends on force of attraction. Stronger force of attraction means higher melting points. So let's do this. Yes. Which one has the strongest? So drop the oxygen because oxygen is the same in all the cases. O2 minus, O2 minus, O2 minus. This is Na plus. They all are isoelectronic. Remember we did the isoelectronic species? These are isoelectronic. They all have two shells only. These are, yes, very good, Amodita. They all are isoelectronic. This is 1s2, 2s2, 2p6. Same with this. They all have 10 electrons. So what to compare then? Nuclear charge. The nuclear charge on sodium is 11, 12, 13. Nuclear charge, number of protons, atomic number. So the highest force of attraction is in Al2O3. So Al2O3 will be with the highest melting point. Mayank, you're understanding this? Then MgO, then Na2O, right? Is there any question here? Mayank and Akash, is this clear? Okay, then answer this question. If I give you Fe2O3 and FeO, which one do you think will have higher melting point? So these are Fe and oxygen. Oxygen is not going to change its oxidation number is 2 minus, 2 minus. What's the oxidation number of Fe here? Plus 2. What's the oxidation of Fe here? Plus 3. Mayank, your answers are not coming. So which one has stronger force of attraction? Fe3 plus or Fe2 plus? In which case charge is more? Mayank, are you there? Come on. In which case charge is more? Here. here. This is going to have higher melting point than FeO. Write on these examples. Higher charge, higher attraction. Higher attraction, higher melting points, right? Very difficult to break this Fe3 plus and oxygen because of the very high charge on Fe3 plus. More charge means more attraction. That you have seen in this equation. Mayank and Amodita, clear? One more. PbO and PbO2. Which one has stronger attraction? Okay, what is the reason? Because in PbO2, it is +4. In Pb, it is +2. +4 means Q is more. So there are plenty of such examples where the metals are identical. Just because of the difference in the charges, their melting points are different. Like there is SnCl2 or SnCl4. Which one has stronger? Yes, this one. So write down these examples. And I have already discussed FeO and Fe2O3. Hg2Cl2, HgCl2. Which one? Yes, this one. Because here it is +2 and here it is +1. This is mercurous, this is mercuric. Okay, so these are famous questions for chemistry Olympiad as well as for AP chemistry. And if you have a good understanding, these are not difficult at all. Okay. So in ionic compounds, we have some different properties of ionic compound. Do you remember I told you about covalent network, graphite, diamond, silica? Silica is sand. Out of these three, which one was good conductor of electricity? Diamond, graphite, silica. Which one was good conductor of electricity? Graphite. What was the reason, Meg? Reason? Moving electrons, free electrons. So who can conduct electricity? This is a very important line which is very strongly tested in every exam. You take one question in AP, you take one question in chemistry Olympiad. Electricity is conducted by moving charged particles. And these moving charged particles can be free electrons, which you can see in metals and which you have already seen in graphite, or ions in ionic compounds. Most of the ionic compounds are solid. Like this is NaCl. This NaCl is solid. Na plus, Cl minus. Can you see how they are sitting next to each other? Na plus, Cl minus, then again Na plus. What can be on the top of Cl minus? Another Na plus. What can be here? Another Na plus. What can be in front? Na plus. What can be behind? Na plus. Why? Because the negative is attracted to plus. So you can see that Cl minus is surrounded by 6 Na plus. One here, one here, one here, one here. One on the top, one Na plus on the top, one behind the plane. Similarly, this Na plus surrounded by Cl minus, Cl minus, Cl minus. One on the top, one behind the plane. So this is called as ionic lattice. So what is a lattice? Lattice you can see in every solid. Solids are defined by lattice because solids have a fixed arrangement. particles, molecules, atoms, they cannot move. So this word lattice is there for every type of solid. Covalent network of lattice, covalent molecules lattice, ionic lattice, metallic lattice. So here this is ionic lattice because here they are arranged in a regular three-dimensional arrangements. It's a very regular, repetitive. Regular, what is a lattice? Regular and repeating. Repetitive. Repetitive. Arrangement. In this case, what is it? Arrangement of ions. Arrangement of ions. In three-dimensional. That's the meaning of lattice. I'm saying ions because we are dealing with ionic lattice, right? So can you tell me why that Na plus cannot be next to Na plus? What's the reason? Why I cannot have two Na plus? Repulsion. So when repulsion takes place, what happens? It's going to break away from here, right? Okay. So now we are going to talk in terms of lattice, ionic lattice. You can see this ionic lattice. This is solid. You can see solid here. Is it a good conductor of electricity, this solid? No. This is solid lattice of NaCl, solid NaCl. So why it cannot conduct electricity? Charges are there. Na plus, you can see the charges, Na plus, Cl minus, Na plus, a regular repetitive arrangement. So why it is a bad conductor of electricity? Yes, please. Ionic solids are bad conductor of electricity in the solid form. Bad conductor. But there is no free electron in ionic solid. Do I have electrons in NaCl? Na plus, Cl minus? No electrons, right? So what is the reason? Yes, Akash, what is the reason? Solid NaCl. Read this line. Do you have moving charged particles? Charged particles are there. Are they moving? That's why. In solid ionic compounds, they are really very bad conductor of electricity because the ions are not moving. Ions, the charged particles are not moving. Right? What about this one? This is aqueous, NaCl aqueous. NaCl aqueous. Here, the charged particles are moving. See, Cl minus moving, Na plus moving. They are moving, isn't it? So, is it a good conductor of electricity? Yes, you can see the bulb is glowing. So, ionic solids in aqueous form, aqueous means in water, they conduct electricity. This is a very, very important question. And this is water, pure water, H2O. Is it a good conductor of electricity, pure water? No. What is the reason, Mayank? Give the reason. Because it's a covalent molecule. There are no free charges. There are no free electrons. There are no free ions which can move in water and can carry electricity with them. Children, this question is clear? That electrons are the electricity is carried by moving charged particles. Now I'm teaching you a few more things about ionic solids. So one thing is clear that ionic solids are solids. Ionic solids are bad conductor of electricity. Ionic solutions are good conductor of electricity. Covalent molecules are bad conductor of electricity, right? And the another important point is they are brittle. Ionic solids are brittle. Brittle means you take any ionic solid and you hammer it, it will break down into smaller pieces. It will break down into smaller pieces. So this is a question. Explain why. Now you have Na plus next to Cl minus, very regular repetitive arrangement, right? When you apply hammer, use hammer. Hammer is force. So when you apply a force, these ions, they get displaced. The ions are getting displaced. Means you can force, this force can put two Na plus together because you are applying force, or two Cl minus together because ions, that arrangement is getting disturbed. So even more negative charges are coming closer. See here, they are coming closer. And when they are coming closer, what happens? Repulsion. And when there is repulsion, the particles will move away from each other. And that is the brittle nature. Brittle nature means when you hammer, they get converted into fine, small pieces, just like glass. When you hammer a glass, what happens to a glass? Particles. Yeah, shatters means brittle. Glass is brittle. The word brittle means breaking down into small particles, right? Small pieces. So this NaCl is brittle in nature. All ionic compounds are brittle in nature. When you apply hammer to this lattice, then the arrangement of ions will get disturbed, and this can force positive. This can force positive, or negative to come closer, which can break down the molecule, break down the lattice. We are good? So I'll be asking plenty of question based on it. Okay. So here is a question. Sugar. Formula is C12H22O11. Salt. Eating salt. Formula is NaCl. Both of them are solid. Can you identify the type of attractive forces in sugar? It has, I'm giving you a hint, it has plenty of OH. So first of all, you identify, is it covalent or ionic? Sugar. Oh no, Amodita. It's not a network. There is no network with hydrogen. Carbon and hydrogen doesn't make network. It's a molecule. I have given you examples of network, only very limited examples. Carbon, diamond and graphite. I gave you the examples. This is not a network. This is a big molecule, but not a network. Yes, because of their specific size. Carbon, silicon, silicon with carbon, silicon with oxygen. Not carbon with, not with oxygen. carbon, pure carbon at diamond and graphite. And then there was one this. These are the only few selected examples. That's it. Only few. Network solids are very less. It depends on their size, small size. So they have high tendency of making covalent bonds with each other. The property is called as catenation, which you are going to do. They are going to get bonded with each other to make big network. But this is not a network. This is a molecule. Molecule with OH bonds. So is it polar, non-polar? Sugar is polar. And is it a good conductor of electricity? OH? How can we tell? Yes. Akash, can you help her? I gave you the hint, OH. What is OH? What kind of attractive forces if OH is there? Hydrogen bonding, dipole, LDF, right? Mhm. So is polar in nature. It has hydrogen bonding, it has LDF, and it has dipole. Salt, NaCl, is covalent or ionic? Ionic. So do you think in the solid form any one of them can conduct electricity? No. But in the aqueous form, which can conduct electricity? Akash, you're there? Yes. So only NaCl can conduct electricity in the aqueous form, right? So understand, sugar is very soluble in water. You add a small piece of, and sugar is very crystalline. Have you seen the shape of the sugar? Very crystalline, like a cube, big cubes of sugar. NaCl is also very crystalline. You put NaCl in your hand, in your palm, and rub your hand. When you rub hand, you can feel the sharp edges of the cubes of the NaCl. Same with sugar. You take sugar in your hand and rub your palms. You can feel the sharp edges of the sugar molecules. So both of them have lattice, but one lattice is ionic, other lattice is polar covalent. It's easy to break this lattice. It's difficult to break this lattice. Okay, moving on. So the reason is clear why ionic solids are brittle, because you can see that how tightly they are packed. They are very tightly packed here. When you apply hammer, the ionic arrangement is getting disturbed, and positive, negative, they are forced to come together, and when they come together, it can split the lattice from there. They fall apart. They scatter away. So that's why they are brittle. So this can be a question. Akash, you have understood? So you have to take care of 2 points here. One, ionic lattices are very tightly packed. Ions are very tightly packed because of strong attraction, plus minus. Second, when you apply hammer, then this arrangement gets disturbed, and this can force similar charges to come closer. And because of high repulsion there, the ions, they get scattered away from each other, which results in breaking down of the lattice into smaller pieces. Okay, now we are on the metallic bonding. So we have understood ionic, we have understood covalent, we have understood the network solids, and now we are on the metallic bonding. Who is going to type the examples of network solids? network, very strongly tested in every exam. Write down all the examples of network solids. I just gave you when Amodita was asking a question. Mhm. Network, covalent network solids. Carbon, graphite, silica, even silicon, not oxygen. Don't say silicon and oxygen. Oxygen is not going to make network. Silicon dioxide. Oh, no, no, Akash. Why you have added sugar? What did I say about sugar? I think you were not listening at that time. Yes, Mayank, is sugar network or what is it? Yes, Amodita. Sugar is covalent molecule. It's not a network. These are the network. Carbon. So, Amodita, don't write O2 separately. Oxygen is not a network. Only when it is with silicon. Only when it is bonded with silicon. These are the only examples which we need to know. Only. You know, you heard about bulletproof jackets? Bulletproof. They are very hard. You heard about it? In the movies, they wear bulletproof jackets. Do you know what material is that? A network solid. Yeah, Kevlar. What material is that? Check that. It's a network solid. And it is of boron and nitrogen. It's a polymer. So that's why we are not learning it. But can you see boron is very close to carbon? It is made up of boron and nitrogen. It's a very close, very similar to network solids. That's why it's so hard that even bullet cannot penetrate through it. Network solids are very hard. So please be clear about your network solids. I'm not giving you this example because in the books generally we are going for these one. This is a kind of very hard polymer. Hard polymer. Poly means many molecules. Similar to network solids. Okay. So now metallic bonding. How metals are attracted to each other. Metals are attracted to each other. They are also solids. What kind of attraction they have? They are not losing or gaining electrons. If I give you sodium metal, sodium is a solid. How come it is a solid? What kind of attraction? So understand in metals, we don't have sodium. We have Na plus. Sodium solid loses one electron like this. You have Na plus. Now in the solid lattice, it is Na plus. If you know in the periodic table, can you name a family with the lowest ionization energy? We have done the periodic trends. Name a family with the lowest ionization energy. Family means group. Yes, first group. First group matters have very low ionization energy. Yes, Mayank. Akash, where are you today? I have made questions for you, but I I've started like there are nearly 24 questions which I have made, but somehow I realized that I can make nearly more than 100 for the same category. You remember VSEPR I was talking about that I'm going to give you 100 questions VSEPR. So Akash was asking where are the questions. So I'm making them. It's taking some time because there are so many molecules and I have to draw the structure also. So don't worry, you'll get it in 1 or 2 days. And for that, chapter 3 is also needed. types of IMF, which we have already done few things. So who is going to tell me that why this ionization energy is very low for the first group? What is the reason? Alkali metals have very low ionization energy. Why? Ionization energy depends on size. Yes, that is also the reason, but it depends on size. Which elements are biggest in their respective periods? What happens to atomic size as you move across the period? Size decreases. So if the size is big, what is the ionization energy? Attraction is less. See, R is more. Size is big, R is more. Attraction is less. That F equals to this equation, Q1, Q2 over R squared. If attraction is less, then you can easily remove electron, correct? So the ionization energies of the metals, in fact, all metals, alkali metals have the lowest because they are biggest in size. So they are the one which can lose easily, very easily. There are two reasons. One reason you people are writing. You are writing the correct reason that by losing one, they can get the nearest noble gas configuration. You are right. That's why they have high tendency of losing. But another reason that they are also very big in size. It's easy to remove electron. You don't require very large amount of energy to remove electron. So what happens that in metallic solids, if I give you 23 grams of sodium, can you tell me 23 grams of sodium is how many moles of sodium? 1 mole. Very good, very fast. Can you tell me in 1 mole of sodium how many atoms of sodium are there? Atoms of sodium? Avogadro's number. Yes, Avogadro's number. If I give you 23 grams, Avogadro's number, you remember, it's a big number. You're typing here, very big number. So it's a very big number. If I give you 23 grams of sodium, then in 23 grams of sodium, you have Avogadro's number of Na plus, Avogadro's number of electrons. Avogadro's number of electrons, these are moving. They are delocalized. You know the word delocalized now, right? Delocalized means moving, can move anywhere. So can I say that, oh, there is a sea of electrons here like this? These are electrons. These electrons are moving, free to move anywhere. And in this sea of electrons, you have fixed position because it's a solid, you see? So positions are fixed. So you have fixed positions of ions like this. They are not moving and they are not repelling also. Who is going to tell me why they are not repelling? They are next to each other, but not repelling because they are surrounded by, every electron is surrounded by, every ion, sorry, not electron, every positive ion is surrounded by a pool of electrons. Everywhere electrons are there. So between these two, sodium plus what is there? Electrons. And electrons are not letting them repel with each other because electrons are satisfying the attraction of the plus with minus. So Na plus are sitting next to each other, in the lattice. This is lattice, solid lattice. This lattice is made up of ions. Which ions? Metal ions. There is no anions here. We don't have anions. We don't have Cl minus, Br minus, like these kind of things. So what is there in place of this Mn? This is fixed. These ions, metal ions, are fixed in the lattice. They have fixed positions. And then what else is there? Electrons. Can you see how every metal ion is surrounded by a pool of electrons? This is called as metallic bonding. In metals, we have free electrons which are creating attraction between the metal ion and the electrons, very strong attraction, metallic forces, right? So here these electrons are shared by everyone. Electrons are moving, delocalized. So electrons are shared by everyone. They are moving. They are moving. Equally shared by everyone. Delocalized. And these are delocalized. So force of attraction is very strong. It is the attraction between multiple electrons and the cation, the positive metal ion. And is it a good conductor of electricity? Metal? Metals are good conductor of electricity? Yes or no? Yes. Even in the solid form. Even in the solid form, they can conduct electricity. Remember, ionic solids cannot conduct electricity, but they can conduct electricity. So this is metallic bonding. So again, it depends on the charge and size. So who is going to have stronger metallic bonding, sodium or magnesium? Again, use the same formula. F equals to K times Q1, Q2 over R squared. Mg. Why? Because it's going to lose 2 electrons. It's very small in small size, with plenty of electrons, plenty and plenty of electrons. So the lattice of the magnesium is more harder than sodium. Now answer this question. Alkali metals, the first group, alkali metals or alkali metals, are soft with low melting point. Explain. Explain. They are very soft. You can cut them with the help of knife. You can cut these alkali metals with knife. Yes, first they are bigger in size, big size, as compared to other metals. Second, one more reason, Amodita. Maximum they can have only 1 plus charge. It's less as compared to other. 1 plus charge. Charge is less. Due to these two reasons, the lattice of the ionic salt of the first group, like NaCl, NaBr, all these, they are, oh, I'm talking about metals, sorry. That's what I was thinking. The lattice of sodium metal, lithium, potassium, rubidium is soft because they are very big in their size, because they are in the first group with the biggest size and the minimum charge of +1. Can you compare their lattice? Which one has the strongest lattice? Which one has the strongest? Yes, lithium. Again, give the reason. Lithium has the strongest, then sodium, then potassium, then rubidium, cesium. So what happens to the melting point down the group? Write down, these are very important questions. Melting point of metals down the group of metals. Down the group increases or decreases? Yes, melting point decreases. Size is increasing, attraction is decreasing. So melting point is decreasing. Which metal is very soft, very, very soft out of these? Which metal is very soft? Here. No. What happened? You cannot see cesium here. Here, this green box is very, you cannot. Oh. Is it visible now? You can see everything, whatever I'm writing, Akash. Cesium is very soft. You know what's the melting point of cesium? I think I told you that it has such a low melting point that you keep it on your palm, it will melt. Of course, you cannot keep it on your palm. It's very reactive. It can give burn injuries. But it's very soft. Its melting point is somewhere around 30 degrees Celsius, somewhere 28, 27, something like that. Metal with such low melting point, right? So melting points of the alkali metals is lowest among the metals and it decreases as the size increases. Now answer another question. Another question, children. What happens to metallic character down the group? I gave you this earlier also in the periodic trends. What happens to metallic character down the group? Remember I explained you metallic character is the tendency to lose electrons. So what happened? It increases. We did this in periodic trends. So which is more metallic, cesium or lithium? Which is more reactive, cesium or lithium? Yes, cesium is more reactive. Lithium is less reactive. So these are Amodita cesium, right? So these are very important question for any chemistry Olympiad. Chemistry Olympiad or AP, any chemistry exam. That's about the metallic bonding. Now you remember I was telling you brittle. What is brittle? Breaking down into smaller particles, fine pieces, and these pieces are formed because when we are going to hammer that substance, you know, when you want to make fine powder, your mother will say, okay, crush it with the help of hammer. And you take some kind of, you're beating it with some heavy metal to crush it, right? So, because they are very tightly packed structures, so when we hammer them, similar charges will come closer, and this can result in that breaking down. Can you give me 1 second, please? 1 second. Hello, you can hear me. Okay, thank you. So now we are going to learn another word. We call it as malleable. The word is malleable. Ductile. Malleable means you can make sheets. You can spread them. Ductile means you can make wires. So if I want to make a sheet of a solid, which solid I have to use? Metals, only metals. Metals are malleable and ductile. Why these metals are malleable and ductile? That we need to know. So they will not break down into smaller pieces. Metals, they don't break down into smaller pieces when you hammer them. So when I'm going to hammer, when I'm going to apply some force and hammer this metal, so here you can see when this plus moves in this direction, what will happen to this plus? It will move in this direction. This will move away. They can move. So these positive charges, they start spreading out. And in between, electrons are there. So repulsion is not getting caused. Only thing that when this plus moves in this direction, this plus moves away. In between them, electrons are there. So there is no very big repulsive forces which are being created to break it from the center or from anywhere. Only thing is that when you hammer, when you apply force, they try to move away from each other, which results in sheets, making of the sheets and wires. So only metals can be used for making sheets and wires because when we apply force on them, they spread out. The ions spread out. Is it okay? And metals are good conductor of electricity. So that's about your different types of bonding. Ionic bonding, covalent network, and then you have covalent molecules. Covalent molecules and covalent network, Amodita, are two different things. And then we have done just now metallic forces. So metals are good conductor of electricity. What is the reason? Metals are good conductor of electricity. Free electrons. Okay, now we are going to spend some time with these covalent molecules and their bond energy diagrams. Okay, ready? You are already aware of these things. As you can see in my notes also. More magnitude of charges, more force of attraction, more energy released. Right? More energy released means more what? Stable. Right? More distance of separation, less force of attraction, less energy is released. More magnitude of same charges, more force of same charges, same. Plus, plus, minus, minus, like this. More repulsion means more energy is needed. You have to understand these three terms. Okay, now if I give you a bond, chemical bond, like this, and another one like this, which bond is longer which bond is longer? Bonds have magnitude, right? This one. And this is, so I'm going to use longer bond, longer. I'm going to say shorter bond, shorter bond. So which bond do you think has more attraction, the longer or shorter? You can take this as R, the shorter. Shorter is more better because here the electron pair is closer to both the nuclei. These are the nuclei. Nucleus has plus charge, so there is very strong force of attraction for this electron pair from both the nuclei because they are very close. R is less. R is less. Attraction is more. So can I say shorter bonds are stronger bonds? Can I say that? And if it is stronger bond, then energy needed. You know, it's a attraction. If I want to break it, then is it going to be endothermic, exothermic if I want to break it? Endothermic. So can I say shorter bonds, stronger bonds, bond energy is high? Bond energy is, what is bond energy? The energy needed to break the bond, or energy released when the bond is formed. So when I want to break the bond, let's say X kilojoules per mole of energy is needed. So that is needed, you need to supply plus X. But when I'm making these bonds, when C and D are approaching to each other, make a bond, bond formation. Bond formation is endo-exo. Bond is attraction, is exothermic. So how much energy is released? Minus X kilojoules per mole, right? So are you clear about the word bond, bond energy, shorter bonds, stronger bonds, attraction, endothermic, exothermic? So write down somewhere. Bond breaking, always endothermic. Bond formation, always exothermic. Shorter bonds, when they are formed, there is big attraction, more energy released. Longer bonds, they are weak. Longer bonds are, so you can make same thing for the longer bonds. Longer bonds, weaker bonds, bond energy is low. So less amount of energy is needed to break them, or less amount of energy is released when they are formed. Okay, moving on, children. Now, I was talking about the bond length, bond energies here. Now let's try to understand how these bonds have specific, every molecule has a specific bond length, a specific bond energy. So what is the reason that molecules have specific bond length, specific bond energy? Like let's discuss this H2 molecule. This diagram is important. There are plenty of questions in AP exam for this on this diagram. Covalent bonding and potential energy. Here is the potential energy. You know the meaning of potential energy? Any one of you? Potential energy. Yeah, what is it? Mayank is standing here. This is Mayank. Here. Yes. Mayank is standing here and Mayank is standing here. In which position Mayank has more energy? In the position A or in the position B? The top. So, can I say that this energy is due to position? Due to position. Why Mayank has high energy here? Because it is attracted by the gravity. It can come down easily with the help of gravitational energy. Yes. Okay, so potential energy you can say is due to position. Position of the electrons, protons, atoms with respect to each other. And here in this diagram, I'm talking about the position of these two hydrogen. They are far away from each other. You can see this line. This line. So this is the distance of separation two atoms. So they are far away from each other, far away. So when they are far away from each other, then there is no interaction. And if there is no interaction, then with respect to each other, their potential energies are zero. Can you see it's nearly zero? It's nearly zero, right? So when atoms are far away from each other, the potential energies are nearly zero, right? But as they start approaching each other, now they are approaching. You can see how they are coming closer. As they are approaching each other, there are two types of forces which will be there. Okay, I'm making here to make you understand. This is the nucleus, and this is the nucleus. This is the electron of the hydrogen. This is the electron of the hydrogen. Understand this. The electron is going closer and is attracted to this positive. An electron is undergoing repulsion also, isn't it? And this plus, this one, is attracted to this electron, but is undergoing repulsion with this plus. So can I say attractive forces, repulsive forces, both of them are working when they're approaching each other? I'm speaking a lot, so I hope you are listening. Akash, Mayank, what are the two forces operating when these atoms are approaching each other? Attractive and repulsive. Attractive between electron and the nucleus of this electron with this nucleus and this electron with this nucleus. That's attraction. Repulsive, electron and electron and nucleus and nucleus. You're understanding this? So when the atoms are approaching each other, the potential energy is going down. So which force is more initially? Attraction or repulsion? Which force? They are not equal. So which force is, when they are approaching each other, you can see that how the energy is going down. It's going below zero. It's released. So which force is more here, Amadita? Which force is more? Attraction or repulsion? Which one is exothermic? Attraction or repulsion? Yes, attractive forces are more. So these diagrams can be there and they will ask you, okay, at this point, what is happening? So you will say there is no interaction. So potential energy with respect to each other is zero. As they are approaching, what is happening here? So you will say they are coming closer because attraction is more than repulsion. But once you reach here at this particular bond length, this particular length, here what happens here? Now you cannot force them more closer to each other. This is the point when the attractive and the repulsive forces are same. Now, if you try to push them more closer, move here in this direction. Can you see what happened to energy? What happened to energy? Sudden increase. What's the reason? What's the reason for this sudden increase? Yes, Akash. After reaching a minimum, when I force them to go more closer, there is a sudden increase in the energy. What is the reason? What is the reason? I know, Mayank, potential energy is increasing. Reason? Yes. Oh no, Akash. That's very wrong answer. Energy increasing. What kind of forces are more than repulsive or attractive? When when energy is going high, what forces are more attractive or repulsive? Mayank, Amodita? Yes, repulsive. I told you here. See, look at this diagram. Here I was explaining you this thing only. And as it is, you know, more attraction means less energy. More repulsion means high energy. So what is happening on this green line? What is green line? Read this part. Because if this point is not clear to us, then we won't be able to answer many questions. Here, no interaction, energy is nearly zero. As they are coming closer, attraction is more, repulsion is less. But at this minima, at minimum point, attraction and repulsions are equal. You force them more closer to each other, then repulsion increases. So there is a sudden increase in energy. Sudden. Akash, can you correct your answer? Amodita, you were right. Akash, can you write down again what happens here when the energy is increasing? Repulsive forces are more. Attractive forces are less. So the bond length is fixed. What's the bond length of hydrogen molecule? You cannot force them more closer. This is the bond length. 0.074. What is the unit here? Nanometer. What's the bond energy? When this hydrogen is approaching, making a chemical bond, formation of bond is exothermic. Yes, that is also fixed. So these bond energies, these bond lengths are fixed because they are decided by the repulsive and attractive forces. So when the bond is formed at that time, attractive and repulsive forces are in equilibrium. They are nearly same, both of them. So now I'm giving you one more important point. You know this size order of the fluorine with chlorine, bromine, iodine. This is a family, right? Halogen family. What happens to the atomic size down the group? Increases. Now remember this line. Big size, big size of the atom. Big size means big orbitals. If size is big, orbitals are big. Like here in F2, the outermost shell is 2s2p. In Cl2, what is the outermost shell? 3s3p. Br2, 4s4p. I2, 5s 5p. So as this shell number increases, this 2 principal quantum number, you remember n value. As n value increases, size increases. So these orbitals are more big in size. And when big orbitals, when they overlap, they make big bonds. Big bonds. Remember that. Big bonds means strong or weak. Longer bond length, weak. Bond energy will be high or low? Akash, bond energy will be high or low? Low. It's very important thing. So you can see here, this is I2. I2 has, you can see the longest bond length here. This one. So look at this diagram. Can you tell me which one is I2? This, this one. Which one is I2? I2 is longer bond. Starting from this 0, which one is the longest bond? This is the longest bond. This one. This is the longest bond. This is I2. This is what is this? Br2. And the last is, the shortest is Cl2. What is the question? Why it is longest on the graph or why actually it is longest? Amadita, you are starting from 0. 0 to this point. Is it more length or this one is more length? Check. Starting from 0. See the distance? Cl2 is more. How come? You are starting from 0. This is more or this is more. Which one is more? The green is more or the red is more? Yeah. Okay. So we are clear about it. So see this line, as size increases, bond length increases, attraction decreases, bond strength decreases, bond energy decreases. So take care of this. Okay. Now I'm giving you another example here. So can you give me the why the order is like this? This is HH bond. This is HF bond, HCl bond. Okay, let's leave this HH. Let's compare these one. So what is happening to bond energy? As you are moving down, bond energy is decreasing. Why is it so? Explain why. Yes, Akash, explain why the bond energy is decreasing. Yes, because fluorine, chlorine, bromine, iodine. I can show you like this. This is important, very important. It will come again in chapter 8 when I'm going to discuss. These are acids: hydrofluoric, hydrochloric, hydrobromic, hydroiodic. These are acids. So this is hydrogen, this is fluorine, HF. This is hydrogen, this is chlorine, HCl. This is hydrogen, this is bromine, HBr. Can you see how the bond length is increasing? HBr. This is hydrogen and this is hydrogen and this is iodine, Hi. The bond length is distance of separation between the nuclei. Which one is easy to break? HF, HCl, HBr, HI. Which one is easy to break? Which one is, do you think, is stronger acid then? Acidity is the tendency to give H plus. So in which case I can take out H plus easily. Yes, that's the order of the acidity also. HF is, this is a very popular question. It will come again in depth. HF is weaker acid than HBr, which is weaker than HCl. HI is the strongest acid. HI. This is the order of acidity. These are very strong acid. These three, they make very strong acid order. Is it okay? Okay, I'm going to erase this now. So you can explain this, but there is few exceptional single bonds. Amudita, you answer this question now. Which one is longest bond? Amudita, which one is longest? Longer bonds are weaker bonds or stronger bonds? So easy to break or difficult to break? So in which case you can easily take out this hydrogen from HI. Okay, now there are few exceptional bonds which are as compared to other, they are slightly weaker. One is F2. Do we have F2 here? Yes. Can you see this? If I compare F2 with Cl2, which one should be longer, F2 or Cl2? Cl2. But actually it is F2 which is longer. Check here. This is F2. Do we have Cl2? Yes, this is Cl2. Oh, what is this? These are bond energies. Yeah, these are bond energies. So which one has more bond energy? Which one is difficult to break? Cl2 or F2? Cl2. Why? Because actually F2 is going to be longer bond. So this trend is exactly opposite to what we were discussing. It's longer bond. Longer bond means less bond energy. That's what is reflected here. Less bond energy. These are some very special cases where we have to see some other factors also. Remember one factor, electron affinity of fluorine is less than that of chlorine. That exception in the periodic trend, do you remember electron affinity? Highest electron affinity in the periodic table is of chlorine. Fluorine, actually we are expecting fluorine, but no, it's chlorine. Do you remember the word inter-electron repulsion? Inter-electron repulsion. Fluorine is very small in size. It has more inter-electron repulsion because of the small size, so many electrons. Electrons are very close. So they repel more in fluorine than chlorine. The same factor is going to play a role here. When you make the Lewis dot structure of fluorine, how many lone pairs are there on every fluorine? 3. Same with chlorine, but chlorine is slightly bigger in size. So it can take these lone pairs nicely. There's no problem. But fluorine is very small in size. Due to very small size, there is more repulsion in fluorine. So this bond becomes slightly longer to minimize this repulsion. So this becomes longer due to inter-electron repulsion. Is it clear? Inter-electron repulsion. How many of you have given the test of the unit 1? Mayank has given. Akash, you have given the test? Okay. Amodita? Okay, you 3, all 3. Good. So I'm going to declare who is the topper of unit 1. Okay, I'll share the report with the parents. All of you are doing good. And it's just that uh, this is just a kind of motivation, not a comparison. I want you to review periodic trends again. Can you do this periodic trends quiz again? Because we are missing many important things. Are we clear that fluorine is longer bond than chlorine? Is just opposite of the trend. But that problem you can see only in these elements over here because they are very small in size. And if they have lone pairs on them, these lone pairs they repel more, which increases the bond length. If I give you oxygen singly bonded with oxygen and sulfur singly bonded with sulfur, so which bond you are expecting longer? Oxygen, oxygen or sulfur, sulfur? Which bond longer? With this exception, you are expecting oxygen-oxygen bond longer due to inter-electron repulsion. Mayank, inter-electron repulsion. Can we check it here? So which bond is stronger, oxygen-oxygen or sulfur-sulfur? Which one bond is stronger? stronger? Sulfur, sulfur. Which one has more energy? Sulfur, sulfur or oxygen, oxygen? Okay, let's see. Where is oxygen singly bonded with oxygen? These are exceptions. Exceptions, okay? Can you see? Do you know hydrogen peroxide? What's the formula of hydrogen peroxide? Yeah. So oxygen singly bonded with oxygen. This is the Lewis dot structure. Do you know that they are very reactive? Why are they so reactive? Because this is called as peroxide linkage. Because energy needed to break this bond is very less. That's why they are very reactive. Peroxides. In organic chemistry, we are always cleaving them from here easily, right? Now answer my question. We are doing exceptionals in single bonds, which you can see only with these three. N single bond N. P single bond P. Which one you are expecting more stronger? Which one is more stronger? Stronger. Yes, PP, this one. Because this is shorter. This is longer. But right now I'm just talking about single bonds, single. Okay, these are single bonds. When we start doing multiple bonds, scenario will change. Okay, ready for the next concept? Oh, this is the same thing. That potential energy diagram, making of a chemical bond. It's a question. Check. Which one is the right diagram? Which one is the right diagram? A, B, C, D, E. Yes. Answer my questions. Why the potential energy is nearly zero here? Yes, they are not interacting. They are far away from each other. Okay. And why the potential energy is decreasing here in this area? Yes. Because attraction is more. So do you think there is no repulsion? Can I say only attraction, no repulsion? Can I say that? No. Repulsion is also there. Very good, Amodita. Attraction and repulsion, both of them are there. But attraction is more. And what happened at the lowest energy point? Here, both are equal. And this is called as bond length. Now you cannot push them together. But if you are pushing them together, what is happening here? Yes, energy increases. So where the nature will stop you? Nature will stop you. Where? Here. And this is called as, this distance is called as bond length. And this energy is called as, this one is called as bond energy. Based on the size, different atoms have different bond lengths and different energy. So what is the bond length of this molecule? You can roughly estimate. Okay, very fast. And what is the energy, bond energy? Slightly more. I'm using the word more, but it's negative. But you're understanding why I'm saying slightly more? Which one is more? This one, this answer is more or this answer is more? Which answer is more? This one. Okay, don't apply your algebra of mathematics here. Okay, here negative means energy released. 400 energy released, 425 energy released. This is more energy released, right? Okay, What's the question here? Okay, can you tell me which one has the strongest bond here? Which one has the strongest bond? Then second strongest, and then next is, okay, so how you're telling me about the strongest bond? From the bond length or from the bond energy? Yes, but which one is the shortest bond? Okay, bond energy wise, you're right. The strongest is z squared. Oh no, y squared. The strongest is y squared, then z squared, z2, sorry, not squared, 2. And then weakest is x2. You're right. But bond length, let's compare the bond length. So which one is the, yeah, x2, then y2, then z2. So x2 should be strongest. Shorter bonds are stronger bonds. So there must be some different story. What's the story here? Check. If I give you F2, N2, O2, can you draw their Lewis dot structures? F2 is F singly bonded with another F, 3 lone pairs. A single bond, right? Single. What's the Lewis dot structure of N2? N2, a triple bond. Yes. What's the Lewis dot structure of O2? A double bond. So now when you are breaking the bonds, here you are breaking a single bond. This is your F2. Energy release is less because you are breaking only one. And this is the shorter bond, shortest bond. Single bond is shortest. But here you are breaking a triple bond. This is your N2. Highest amount of energy is released. And here you are breaking a double bond. This is O2. You are understanding this? So because of the nature of the bonds, they all are not single bond. If I give you single bond, then it will follow exactly what we were discussing. Longer bonds are weaker bonds, all these things. But here we are breaking multiple bonds. So multiple bonds will become more stronger. Can you identify the hybridization of fluorine here? What's the hybridization of fluorine here? sp? Oh, come on. For the hybridization, you're going to count the groups, atoms and lone pairs, sp3, one atom, 3 lone pairs, isn't it? What's the hybridization here? sp. What's the hybridization here? sp2. Remember, lone pairs plus atoms. How are you going to do those questions? Which I'm making, 100 questions I'm making for you. Lone pairs and atoms. So, which one do you think is smallest in size in orbital? Don't you remember that sp3 bigger orbitals than sp2, which are bigger than sp, because here you're mixing more, 4 orbitals. If you remember, I gave you the shapes also. This is sp3, this is sp2, and this is sp. So nitrogen has the very small size of the orbitals. So that is the reason the bond length is slightly lesser than O2 because of the triple bond. So many factors, they start playing together. That is the reason the order is not the order which we are expecting. Is it clear? So which one has the strongest bond? N2, O2 or F2? Which one is least reactive? Least reactive. And is an abundance in atmosphere. N2. N2 is very stable molecule. Nitrogen gas is totally inert in nature, very less reactive. Okay, so understand the reactivity also. If the bonds are stronger, reactivity is less. Okay, work out the hybridization here. What's the hybridization of this carbon and this carbon? Yes. So in the first case, sp3 carbon is chemically getting bonded with sp3 carbon. What's here? In the second case, sp2 carbon is chemically bonded with sp2 carbon. Both of them are sp2. You can check. Here, sp carbon is bonded with sp carbon. So which one is the shortest bond you are expecting? Which one is the shortest? Yes, and it is the shortest and the strongest. This is your triple bond, this one. This is C triple bond C, highest energy. And this one is C double bond C. And this one is C single bond C. I'm changing my question. Try to answer it very smartly. All ears here. Question is getting changed. It's very easy to identify single, double, triple. Definitely single is weakest, double is stronger. Now the question is, in which case the carbon hydrogen bond here, here, or here, which carbon hydrogen bond is strongest? Hmm. Hydrogen is same, 1s in both the cases, 1s, 1s, 1s. What is changing? Carbon. So which bond you are expecting longer? Which bond are you expecting longer? sp3 carbon with 1s of hydrogen, sp2 carbon with 1s of hydrogen, sp carbon with 1s of hydrogen. So which one you are expecting longer? Yes, in ethane. Yes, because these are bigger orbitals. Big orbitals, big bond lengths, right? So these are questions, organic chemistry, college level, they cannot answer it because the concepts are missing. So pay attention to the concepts. Everything is related to attraction, repulsion, sizes, how closely they can come to each other. Okay. I think same kind of potential energy diagram is there for ionic compounds, right? So when they are far away, what is happening? No interaction. As they start approaching each other, what is happening? Attraction is increasing. But this is the minima, right? Minimum. So when the distance of separation between these two is this much, at that time the attraction and the repulsions are equal in each other. You try to force them more closer, repulsion increases. We are good with this? This diagram is okay? Is this red line correct? This red line, is it correct? No. Which one is correct? This one. Because once they are coming closer at that time, they are plus minus, very strong attraction. And when attraction is there, energy goes down. Okay. So I have already explained you the lattice of the ionic solids. You are going to answer the questions only. Ready? Ionic lattice, we have already done. Which one do you think represents Kf? Yes, B. Because it's solid. These are wrong, right? And this one is gas. Kf is ionic and they are saying solid. See, they are writing solid also. So definitely it is very tightly packed ions. Okay, answer this. This is solid Kf. So which one is solid KCl? So try to make out the difference. K will be same. The difference is F and Cl. So which one you're expecting? Yes, A is the answer. Because Amodita, Cl minus is bigger in size than F minus. So K plus take the same size. But Cl minus should be slightly bigger than what is given here. Right? This is out. Is there any problem with this? Yeah, this is out because K plus is still the same. It should be the same as this one. So out. A is the answer. Very simple questions. Yeah, so now let's see the definition of lattice energy. Like ionization energy has a definition. Electron affinity, that is also an energy. It has a definition in the periodic trend. Similarly, we have a well-defined definition for lattice energy. Read the definition. According to this definition, if you take read this one. If you take isolated gaseous ions, isolated, far away from each other, and gaseous, no other attraction repulsion. So when isolated gaseous atoms, when they approach each other and make a solid, is it endothermic, exothermic when they are approaching and making a solid? Exothermic. The amount of energy released, which I'm going to call it as delta H lattice, delta H lattice. That amount of energy released is called as lattice energy. That's what they are writing. So it is the energy released when 1 mole of the lattice is formed from completely separated ions. This definition is very important. And the reverse of the definition is here, reverse. If I take 1 mole of solid ionic compound and separate them into isolated gaseous ions, then the amount of energy needed is called as lattice enthalpy. Okay, Meg. So this is positive and this is negative. So minus delta H lattice is equal to plus delta H lattice. Agreed? Energy can neither be created nor be destroyed. So whatever energy is needed to break the lattice, exactly same energy is released when the lattice is formed. Is the word lattice clear? Can you answer some questions? And this lattice energy depends on that Coulombic forces of attraction. It depends on that formula F equals to K times Q1 Q2 over R squared. Can we do one question here? Can you explain why? Why the melting point of KCl is more than KBr, which is more than Ki? Explain. Use this equation. Yes, because Cl minus is smaller in size than Br minus, which is smaller in size than I minus. So this R is increasing. If R increases, attraction is decreasing. Yes, yes. Very good, Akash. Perfect answer. So, answer one more. Lithium fluoride, you can see, very high melting point. And sodium chloride, explain why. In lithium fluoride, your cation and anions are very small in size, whereas in sodium bromide, sodium chloride, cations and anions are bigger in size. So, any questions from lattice enthalpy? You can compare, you can answer all the questions about the lattice. Okay, simple question. Now, I have to do this Born-Haber cycle. I think metallic solids, I have already explained you, ionic solids, all these points we have done. Okay, these are the few things which are left. Few things are left, which I'm going to cover in the next class. But yes, can we do this Born-Haber cycle? The name is Born-Haber cycle, but AP is not going to trouble you with this name. No one is going to trouble you with the name. But is practicing with the name is much more easier to retain. Meg, you are back. Okay. So this is very important cycle. Let me see if I have this classic whiteboard. Yeah, I do have. So I'm going to teach you this Born-Haber cycle here on the whiteboard. It's very interesting. Everything you know. Now, how to calculate lattice energy for a compound? They have given us an equation. I'm giving you one equation that there is lithium solid reacting with your F2 molecule, which is a gas. You know, fluorine is gas, giving you lithium fluoride, which is solid. I'm making 1 mole of this, 1 mole. And I'm going to call this as delta H naught reaction. Now we are going to convert this into multiple steps and we are going to calculate delta H lattice out of this multiple steps. If I want to carry out this reaction, the very first thing, I'm making Born-Haber cycle. Now very carefully see what I'm doing. First, I'm going to convert this solid into gas. What is it called as? Solid to gas. What is the change? Delta H sublimation. H means heat. Delta H means change in heat, change in energy. Delta H sublimation. Then I'm going to convert this lithium gas to lithium plus gas. What is this energy called as, children? We did this definition in periodic trends. It's called as ionization energy. Delta H ionization energy. What do you think? Sublimation is endo or exo? Solid to gas. You are breaking attractions or attractions are made. Solid to gas. Solid to gas. Breaking. Endo. Energy needed. Agreed? Gas to ionization. Ionization energy. Endo. Remember, energy needed to remove the electron. We are breaking attraction of the electron with the nucleus. Now stop here. Now let's see what we have to do with F2. First, we have to break the bond. When you break the bond, it's already in the gaseous form, so we need not to convert that into gas. It's already gas. So I'm going to break the bond. So I'm going to break half moles. This is half. So the bond enthalpy, right? The energy needed to break the bond, that is delta H, bond energy. But this is for half mole of the molecule, so divide by 2. Is this endo or exo? This is endo or exo, bond breaking. So put a plus sign here. This is plus. Now I'm going to add an electron in this. Add an electron. Remember the term? Adding an electron in isolated gaseous atom is called as? Yes? Periodic trends, electron gain enthalpy, or electron affinity. So this is delta H, electron affinity. Is it negative, positive? This one. All the electron affinities are? Yes. Is this electron making an attraction with the nucleus or you're breaking the attraction? Yes, please, Mayank. Amodita. Periodic trends. This is your homework. Do it again. It's negative. It's exothermic. Do the periodic trends again. I want to see quiz on periodic trends again from all of you. Then I'm going to declare who is the topper. This is F minus. Now this electron and this electron, they cancelled out, right? This is losing, this is gaining, cancelled out. Now you can add these two. When you add these two, what happens? You are getting this solid. You can see this line. These two are added together and I'm getting the solid. These are isolated gaseous ions. What is this energy called as? Delta H. Lattice. Lattice formation. Is this lattice formation endo or exo? It is exo, negative. Now I'm carrying out this reaction, the reaction which is written here, in multiple steps. Then if I show you this, so I'm writing here, the first step, lithium solid, giving you lithium gas. Delta is sublimation, and you're going to say it's positive. Positive means endothermic. Then lithium gas to lithium ion, and that's you're going to say delta HIE. This is also positive, endo. Then fluorine, I've taken half mole because I want to make only 1 mole of this, is F gas. This is delta H. Bond enthalpies, bond energies, bond enthalpies are given per mole. So divided by 2. Whatever value is given, divide by 2 because you have taken only half. Then this fluorine gas gaining 1 electron, giving you F minus gas. This is you're going to call it as a delta H electron affinity. This is negative, this is positive. Then this lithium plus gas, the last step, this one, plus F minus gas, giving you lithium fluoride solid. And this is also negative delta H lattice. Can you add all these reactions? Just see that I'm adding them. When I'm adding, whatever is there on different side, like this lithium gas cancelled. This one electron cancelled. They are on different sides. This F gas cancelled. This F minus cancelled. This lithium plus cancelled. What is left? Can you tell me what is left, which is not cancelled? This we are going to learn again as Hess's law also. In unit 6, Hess's law. When you add, their energies will get added. Yes, Akash. Isn't it that the equation which is written on the top? And that is delta H reaction. So what is delta H reaction? Delta H reaction is the summation of all these energies. Is delta H sublimation, which is positive? Is delta H ionization, which is also positive? Is delta H bond enthalpy divided by 2 because we are working for 1 mole, minus delta H electron affinity minus delta H lattice. This is Born-Haber's cycle equation. It depends on what type of compound you are making. Now in the question, they will give you these values. This value, this value, this value, this value, this value, and they will ask lattice. Or they will give you lattice, means how many terms are here? 1, 2, 3, 4, 5, 6. Out of 6, 5 will be given to you, and they will be asking the sixth one, unknown. You can calculate ionization, you can calculate sublimation if you know the other things. So because the time is up, but I'm going to show you one question, children. Just give me 1 second. We are not going to do it. So in the next class, we'll do these type of questions and few more things. And I think within 15-20 minutes, this unit 2 will be over. Okay. So I see you then in the next class. If you have any questions, you can stay back. Welcome. Welcome, Amrita. Yes, Mayank. What's your question? You can unmute. You can talk to me. Which quiz results? Quiz results you can see there only. No, that's what I'm going to say. I'm going to declare it. Okay, I'm going to declare for all of them together. That's what I said. So the test, unit 1 test will be declared before the next class. Okay. Periodic trends. Repeat periodic trends. Okay. See you then. Bye-bye.